this on record or not? Okay, so okay, yeah, I'm gonna start. Yeah, yeah. So I will mainly talk about monopoles and the electromagnetic ball. Okay, first here some basics, and I'm hoping that most of you are familiar with electrodynamics, at least at your high school level. So as you know that Maxwell's equations describe these electrodynamics that with electric charge being very fundamental, and this electric and magnetic field and coupling between these fields produce some electromagnetic waves, and your visible light is example of that thing. So the way to know an electric field of a Gaussian surface is by Gauss's law, which also bounds the electric flux by the electric charge of that quantity. Uh, However, in Maxwell's equation, we find that there are no monopoles. As this special equation is zero, this integral is zero. Uh, uh, for some of you, you may know this as a Gauss's law in magnetism, and this means zero. That means that there is no monopole. To give a very simple thing, a simple example, a dipole is one where there is a north pole and a south pole. Like see, whenever there is a magnet, there is always a north pole and a south pole. A monopole would mean a discrete, fundamental, unique magnetic charge. Similar to the electric charge, that's just like there is an electric charge E, there should be a magnetic charge. You know, for our purposes, we will denote it by G, the letter G. However, a careful survey of Maxwell's equation begs for monopoles and their existence. What if one assumes for the symmetric Maxwell's equation? In electrodynamics, at least as your high school level, they say that there are no monopoles because of this integral going zero. But if, if if you read Griffiths, and I think Griffiths mentioned this in his electrodynamics books, that there is a symmetry between these Maxwell's equations and this uh, Maxwell's equation. I will show you that symmetry in a moment. So what if there is a monopole, at least theoretically, and how that impacts the overall physics that we have in what goes from here? We will mainly concern with the mathematical descriptions of monopoles. As of yet, they have not been found in laboratories or in particle accelerators. However, for those who are interested in phenomenological aspects, there have been a very few data around monopoles, and you can read these papers. And actually, I must tell you that monopoles is a very integral part of phenomenology, like just like axion physics and all. For those who are interested in physics, you may know there is an axion physics and dark matter research is going on, CMB and all. They find these kind of monopoles data, and you can read around them. But in this talk, and if whatever I'm going to talk, we are not we are not going to discuss experimental verification of monopoles. Actually, in grand unified theories and in quantum gravity, you should expect monopoles beforehand, actually. Even in some parts of the theory, we assume the existence of monopoles by default. There are also hypothetical particles called diodes, which has both electric charge and magnetic charge. But that is not the subject of this talk. Well, actually, diodes and there's also a thing called BPS states, but these are not the subject of the talk. But I'm just letting you know that there are good experimental and phenomenological aspects of monopoles, which, in case you are interested, you can see. The main objective of this talk is to deliver the motivation about a very simple model of monopoles and how advanced mathematics can appear in such models. We will also see the electric magnetic duality and its string theory counterpart, which is called S duality. Some of you must have heard S duality. It's a very famous duality. Yeah, so this is Dirac monopole, and this is by far, you can say, the first theoretically consistent model of monopole. So in 1931, Paul Dirac wrote a paper on consistent monopoles in electromagnetic field with Dirac strings, which implied a quantization. So we will get to know what these words mean. This was a hallmark idea in the study of monopoles. So this monopole was an example of abelian gauge theory, U1. So for those of you who do not know what is abelian, so abelian literally means commutative. For a abelian group or abelian matrix, let's say, let's just stick with matrix now. So if there is an abelian group, the elements of that group would be commutative, if you know what I mean. Like AB equals BA. And for the non-abelian, it is the opposite. So the abelian gauge theory U1. U1 is a group. Okay. So let us see what is a gauge theory first. And this is not related to what is monopoles, but gauge theory is a very important part in physics and mathematics too. So let me just first take a digression to what is gauge theory. So a gauge theory doesn't change under gauge transformation. Actually, let me just tell you, if you have anything to ask, you can just unmute and ask, okay? So a gauge theory doesn't change in the gauge transformations. For example, quantum electrodynamics is a gauge theory. And gauge theories have a very big importance in quantum field theories and mathematics. So if you don't know what is a gauge theory means, like if you have a very, okay, I will come to that a picture. But a very simple example is to consider a manifold or a topology, whatever you want to say. Place an electric charge somewhere. There would be some Lagrangian, and let us suppose that we vary the Lagrangian throughout the manifold. Since this was a gauge theory, Lagrangian could be invariant. I'll come to what this all means. For those who do not know what is Lagrangian, uh, Lagrangian is a quantity of a theory. Okay, it's a very important quantity of a theory. Like you have a Hamiltonian of some theory, you have Lagrangian of some theory, and it's basically kinetic minus potential of the theory. But it's not necessary to understand. But gauge theory means that if you change the theory from one place to another, the theory doesn't change. Let's take a house. If you have multiple rooms in a house, and if you have one theory in this house, let's say you have electromagnetic theory in this whole house, and if you come from room A to room B, the theory doesn't change. This was called a gauge transformation. Changing from one to another room is called gauge transformation. So local gauge transformation, local transformations, if you might call. So in simple words, local transformation which doesn't change the theory itself is called gauge transformation, and theory is called gauge theory. So, if you read papers, theoretical physics papers, there is always a term setting the gauge and all. I think even in literature, you might find the term gauge. So gauge means fixing something so that, changing room to room A, from room A to room B, you shouldn't be bothered with all of these transformations. Okay, here is a very simple example. So if you see let's say this is some topology or a manifold. Manifold, if you want to just think of a sheet of a paper, and let's say there is this area, and let's say there is this another area, and I'm defining a term, let's say lambda here and lambda dash here. This can be anything, vector potential, field strength, electric field, or whatever. So if I change from here to here, this should be related by something. So lambda and lambda are related by the gauge transformation. And this is called conjugation. This G is the gauge transformation. Now, of course, this will need you to go through, and for those of you who are not aware with quantum field theory, you need to go through this, that G's are the gauge transformations, and these are the coming from the gauge group, which in this case was U1. In very simple words, whatever quantity you are taking here and whatever quantity you are taking here, they should be related by it if the theory is gauge theory. And how they are related? They are related by the gauge transformation. And they are related in this overlapping region, this lambda and lambda dash. So if you set the gauge, then lambda and lambda dash are equal. But setting the gauge also introduces ghosts and all for those who are interested. Yeah. Yes, Vago?
Yeah, so these lambdas are basically local charts. So basically, these are just defined for every
No,
pole
no, no.
in some
Yeah,
sense.
yeah. This local charts are these circles. Local charts are these circles, and lambdas are defined on this chart. So, similarly, you can define on this manifold many local charts, and all of these quantities will be related to each other by these gauge transformations.
Right. So gauge
Got
transformation
it?
tells you how to move across these, like how you work with these overlapping regions. So it tells you how to go
Yeah, yeah,
across from
yeah,
point to
yeah.
point in a sense.
It tells you how two different quantities are equal in some overlapping region. Okay.
Right. Cool.
Yeah. So one can also set a gauge like Lorentz gauge in electrodynamics. And this I think undergrads read as well. What is a Lorentz gauge in electrodynamics? More examples of the gauge theories are QCD, electroweak, and well, even general relativity is a gauge theory. So, and this is very actually when I first understood what is meant by gauge theory, and when I first understood what is meant by general relativity as a gauge theory, it's very profound. I will suggest you all to take a look at this. However, there are subtleties with that statement. Mathematically, a gauge theory is basically a principal G bundle with a connection and a curvature. This is incidentally how Young and a few mathematicians described gauge theory at first. For this talk, we do not need to understand. Actually, I just wanted to tell gauge theory is not just a physics idea, it's a math idea as well. And Young, Mills were very famous guys. They were famous guys and they described gauge theory. And actually, incidentally, parallel to them, there were also a few mathematicians who described gauge theory in this language, the principal G bundle. Now, for those of you who want to know the basics, there is a good book by John Dash. It's called Gravity, Knots, and Quantum Gravity, something like this. If you search, you will get to know. Yeah. Now, coming back to the Dirac monopoles, can somebody let me know how much time do we have in this?
For this specific meet, I believe we have 1 more minutes left.
Okay. Okay. Yeah. So, coming back to the Dirac monopoles, we first assume the symmetric Maxwell's equations and take the R3. R3 is just your normal three-dimensional real space, okay? By symmetric Maxwell's fields, we mean that replacing E to B and B to minus E will not change the Maxwell's equation. So if you know the Maxwell's equation, there are these four Maxwell's equations, very famous. And in those four Maxwell's equations, if you change E to B and B to minus E, nothing should change, And if these things are there, we can start. And we do not assume any specific source here. For those of you who solve the Maxwell's equation, there is a source called J. We will not assume any specific source here. Go through Griffith for a simple application. So in this R3, we then place a magnetic charge at the origin, which will produce a magnetic field, which will be of this, G by rho 2. And this G is this the magnetic charge. Just wait for a second. Yeah, sorry. Very sorry. Yes, so in R3, can you hear me? Can please anybody let me know?
Yes, yes, can you?
Yeah, sorry. So in R3, we then place a magnetic charge at the origin, which will produce a magnetic field of this strength. Now this will produce a singularity at the origin. What is meant by the singularity are come, and there are no viable solutions at this origin. But actually, you can just see from here. if this magnetic charge is at the origin, and if we take rho goes to 0, this is a singularity of this magnetic field. Okay, this is very simple. So in mathematics, I think you are told what is a singularity and a pole. This is just that singularity. Okay? There are no viable solutions at this origin. Okay, yeah, this is telling me that running out of time. We will come again to this meeting link after 10 minutes, after this is over, okay? Now a suitable topology is R3 minus 0. So if you don't know what this means, you just take the three-dimensional space and you delete the minus. This is the 0, the origin, which means that R3 minus the origin. So the B produced a magnetic field on R3. And remember, this is all for symmetric Maxwell fields. This is not for ordinary Maxwell fields that you are taught in, at least in undergrads. Okay. So the B will produce a magnetic field on this topology, which is R3 minus 0. But this is not a viable topology. This is still not viable topology. And Dirac modified this in order to have a consistent field. For those of you who want to know why this is not viable, and this is going to be technical, because there is no global potential which you can describe on this R3 minus 0. You need open subsets. I will come to that. So a word about R3 minus 0. So R3 minus 0 is a very interesting topology. It is also boring. It is just a regular three-dimensional space with origin delete. Now, any two paths are homotopy equivalent on R3 0, and any loop can be contracted to a point in R3 0. So it is fundamental group is trivial. Such a topology is called simple. This is not valid in the case of three sphere. Now, three sphere is just a three-dimensional sphere in four-dimensional space. So, and by fundamental group, this if you read homotopy theory in mathematics, you find this thing, fundamental group. It actually tells you how many ways are there to construct a loop in some topology. So any loop in R3 can be contracted to a point, and any two paths are equivalent, homotopy equivalent in this. So basically, if you have two paths, let's say this is a path and this is the another path, and by lambda and lambda dash are two paths here. So when these are homotopy equivalent, and these are in actually in R3 0, these two paths will be homotopy equivalent. So these are homotopy equivalent. That means I can say these are equivalent paths. This is what is meant by homotopy equivalent. And this condition is not valid in the case of three sphere. This thing is homeomorphic to two sphere. For those of you who know what is homeomorphism, this R3 0 is homeomorphic to two sphere. But three sphere is not a simple connected. Simple connected means these should be satisfied. And examples of non-simple connected topology is this. This is a torus, and these are some topology with genus. So if you can see, there is not every loop here can be contracted to a point. For example, if I take this loop, a loop around here, it will not be contracted to a point. While in R3 0, any loop can be contracted to a point. In this as well, this is a torus, and here also you will not encounter such thing. So these are the examples of non-simply connected topology. Again, getting back to the Dirac monopole. So the resolution to the singularity was Dirac strings. Now we have this R3 0. Here we have this R3 0, and at the origin we have this B magnetic field, but Dirac had to use Dirac strings in order to get the quantization conditions, which will be explained. This is a little technical to explain in this talk, but I have tried. I will not explain in detail, but I have tried. Anyway, in order to have a viable topology, Dirac suggested a string which originates from the origin and moves to infinity without intersecting itself. You can just imagine an origin and a string going vertically to infinity. Now, this is a very technical thing. For such strings, we can define its complement as open subsets in R3, which has pi2. Pi2 is a different thing. It's a fundamental group. This suggests that no sphere in U contains the points of Dirac strings. Moreover, U is simply connected as well. So we can take a loop around DS and continuously lift around the origin and shrink it to the point, because these are simply connected, and any loop can be contracted to a point. We can imagine two Dirac strings with a common origin, one going upwards. For example, if this is a string, this is the origin, this goes upward, and this goes downwards. Two Dirac strings, and we can get two open subsets which are complement of these Dirac strings. So complement should be obvious. And this will cover the whole R3 minus 0. This is obvious. We can now define two potentials. Potentials, I hope, for those of you who have taken electrodynamics, even in 12th grade, there's a term called potential, and we are talking about that potential. So these two potentials will be described on two sets, which is U plus and U minus. And I will denote it as A plus and A minus. Now the thing is that these two are not equal, which you might expect, because it is a R3 minus 0 and this should be equal. There should be just one A, but that is not found here. There are two A plus and A minus, and they do not agree on the union of this. Sorry, on the, yes, which is just this R minus chance. If they had agreed, this means an A global. This is not for this, but actually there's a very good issue that A is not global. You have to define A local, and they are related by the gauge transformations. For this configuration, F is exact since this, and this is resolves somewhat the problem of singularity. However, this is not the Nexus solution. This was technical, I assume, but this is how the singularity can be avoided. Anyway, the point of Dirac monopole was to introduce a quantization condition. What is meant by a quantization condition? Now, if an electron travels in the electromagnetic field we have described by putting that monopole at the origin, then it will observe monopole only when this path integral is satisfied, which implies this condition. Now, for those of you who do not know what is path integral, it's not important here. This is important. Eg equals n by 2. Now, where n is an integer, E is this electric charge and G is this monopole, magnetic charge. And this is the result of this Dirac monopole. And this condition that magnetic charge should be 1 by 2 E value is called the Dirac quantization condition. This quantization condition requires that all magnetic charge should be multiples of 1 by 2 times E. So if this is satisfied, then it means that G should be an E by 2. You should take this to here and it becomes an E by 2. Similarly, it should be E equals, G, sorry, what I'm saying. Yes, you should just remember E and G's are inversely proportional. And they should be integer multiples of their opposite charges, okay? Now, equivalent is saying the round and round that if there is a magnetic charge, then the electric charges should be integer multiples of 1 by 2G. So if there is an electric charge, then the magnetic monopoles should be in the integer multiple of that electric charge, and there should be other round as well. I think this meeting will end. So we will continue after 10 minutes. I believe it will end. Oh, it didn't. Okay, anyways. So equivalent is saying, okay, let me emphasize this because this is very important. It is saying that if there is a magnetic charge, then the electric charges should be integer multiples of this. That means that electric, if you read physics, you know that the electric charge is very fundamental. That there is a term called quantization of charges. That every charge in this universe can be written as n times E, And but if there is a magnetic charge, then the electric charge will be integer multiples of this 1 by 2G. Which is to say that G being fundamental now, E is not fundamental anymore. Okay, this is a very interesting condition. This means that the existence of a magnetic monopole implies the quantization of the electric charge. But I mentioned that it was not a very good solution, this Dirac thing. And there came many more solutions actually. Famous of them was O-Young monopole. This was rather based on Blaze theory and gave a quantization condition based on local potentials described in two charts on a two-sphere. Now, this is very technical for this talk, but the reason why a global potential doesn't exist is because of the Stokes theorem. And I think this is available in Dirac's paper as well. So if the magnetic charge is there at the origin, if you solve this law now, you should get 4 pi g. This is for symmetric Maxwell's equation, and this is just a Maxwell equation, okay? However, a smooth